Hi, Professor.
Okay, Emma.
How are you?
Yeah, doing good. How are you?
I'm good, thank
Let me
you.
go to the hospital.
Sure, sure.
Yeah. So, right, so that's what we started earlier.
Our
So
meeting
the
is at
meeting,
1:30.
I thought you were two.
No, this semester
But
you
I
said
told you already,
1:30.
got it all. I forgot.
Yeah.
I shortened the meeting time to
Yeah.
half an hour. But I still
Yeah, you
think
said
about
last semester.
this. Yeah.
That's fine.
Anyway, yeah, good. Thank you. So
Yeah, sure.
let's see. You can share your screen.
Yes, sure. That's good. So, since our last time, I modified all the figure set for this paper. So now they're almost like ready. It's only the last one. So this is the new set of the figure one. Um, I just need your comments if you need, like, we need to change
Okay,
anything.
sure. Then give me a couple minutes.
Sure.
Um,
The description is not correct right now, but it's only the figure set.
good. But, delete the design.
Why?
Just the schematics of the dog bone specimens.
Mm-hmm.
The design.
So the different thicknesses you mean?
The design, this one, what I meant. Delete this. Delete this.
Okay.
Because it's not only design, right? Also manufacturing. Manufacturing. These two green, what are these two represent? This is this.
What do you mean?
This one and this
Oh,
one.
these are the UV light.
Oh, I see.
It's here, like.
So, the tree, I'm trying to see the tree was actually, that's the printing, print head. Oh, so, I see. So, where does this image come from?
I made myself.
Oh, okay. So those are not specimens, right?
No, these are the
Yeah.
different materials that inject the droplets.
So you mean the tree is actually here?
Yes.
Am I right?
Yes.
I see.
So like first the material is injected here, then the flatten rot like after the material is injected, the flatten roller will flatten the surface before the light will cure the materials.
Oh, I just have one small comment. Maybe we add the tree underneath.
I have it in another
You have it, okay.
yeah, in another one, so I will show you.
And then the C become automatic, right? So you have
Yes.
this part view of the tree.
Mhm.
Right, and then you can put an arrow here saying this is the tree, right?
Like where? Under the print
I
head?
mean, right, it's here. So this is the tree, am I right?
Yes, the tray is
This
here.
is the tree.
I will
And then you can say this is to print the tree, right?
okay.
And you can draw, yeah, draw or not draw, that's fine.
Okay, I have it.
You already have it.
Let me show you here in the next slide. So I think here I have it here. So the dog bone will be where I can add the print head
Yeah.
if you want here.
My question is, my suggestion is if you go back, it's
Mhm.
not necessary to be a very, it's just a schematic
Okay. Okay.
of the tree, right? Not necessary to have all those details. So for example, it's just a surface people will see.
Okay,
right?
sure.
Then they won't ask the same question that I'm asking.
Yeah, the location.
Otherwise, at the very beginning when I see this, I was thinking those are like a printing pad, right? Print head. The print heads are spiking.
Oh, okay, okay.
Yeah, so, I mean, for me, I'm already know printer very well. Well, even me will misunderstood in the way like that. I'm just trying to say to say like if we add the tree, the everything will be
Okay.
super.
Okay.
Right. That's avoid those unnecessary misunderstandings
Sure.
could come from the reader, right? And the reviewer, right? If the reviewer cannot understand, we don't even have a chance to explain to them.
Yeah.
Right? Yeah. Yeah, yeah, that's great. This is a very nice figure. Yeah.
The next one is
Oh,
this one.
one
Yeah,
minor
sure.
comment. We keep the font size the same.
Yes, I in all figures like either it's 9 here or 10. Like I kept it the same.
I mean, here should be Times New Roman, right?
Yes.
This is not Times New
This is
Roman.
not. Oh yeah, this is old one. Yeah, the rest are time.
Yeah, perfect. Then other than that, that's perfect. Yeah, yeah, very good. Very good.
And this is the
That's
next
it.
one.
And this is second one.
Mhm.
Yeah. Oh, T, did we clarify in the previous slide what is T? If we go back to the, right, then mark the T there.
Here, okay.
Yeah. Then we don't need to do anything later. So when people go to the T in figure 2, they know it means that, right?
Okay.
So you mean the T for the soft and T for the hard and
Yes.
thin, right?
Yes.
Then you mark them.
Okay.
Right, for the yeah, good. Next is this one. We have this point 2 and T equal to. Oh, can we go back? Oh, yeah, you have that. You have that very right. maybe here, add, see, like the legend that you showed in the previous one, right? You add, see, black and white, right? Oh, white is hard to how people will know black is the tango, you know?
Oh.
You can, because white is hard to,
Yeah.
or you can just write in the legend, you know, for A, the caption, the figure caption A, after
Okay.
A, you put a parenthesis, then put a parenthesis, white is white, and you can directly change there.
In the
Here.
description, right?
Yeah, the caption, the figure
Oh,
caption
yeah.
here. Yeah, add here a parenthesis. Right.
Okay.
And then you say white layer is the tango or white, and then the black layer is the androgyny black, right?
Okay.
The print is 3D printed solvable specimen from to be honest, I don't know why, but my advisor, when I use testing, she always changes into experiments.
Oh. Yeah. Okay.
She thought that's more formal.
Okay.
Well, I don't know actually. So then I continue doing this to my students as well. Right? I think.
Okay.
Yeah, mechanical experiment. And samples usually using
Specimens.
She corrected me. Yeah, she corrected me. That specimens.
I interchange them, like one time specimen and one time sample. You see here.
Right.
Like,
I
I don't want to.
Yeah, I don't know whether it's so important. Maybe it's just her habits, right? Well, she thinks, while others she thinks is more formal. Like specimen and the experiments are more formal.
Okay.
Well, maybe not everybody agree with you, but that's her opinion.
Yeah. Specimen. Okay.
That's a small thing. Going to area showing printed layer aligned with the loading direction with different increment thickness. Right. And the T, those mathematical symbols always be italic.
Okay.
T, beta, right? And the millimeter, they are always italic, while the numbers are always normal.
Okay.
They are visible in grid printing line. Is likely showing printing direction. Printing line on a specimen feel consistent with printing direction. Being consistent, but change showing into being consistent.
Okay.
Being consistent with printing direction. And here, to further clarify, it's beneficial if we draw by the beta angle. Makes sense? So, which is beta? This is 60 degrees, or
No.
This is beta? No.
This is from here to here. Like, you see X in here.
Right. The market, right? Because when you align your specimen and when you put your specimen on it, you will need to know which angle is beta, right?
Yes.
So which angle is with this angle, right?
Yes.
So this is beta.
I have it here. I'm not sure. That's why
Right. I know. You think it's clear, while people still not super clear,
Okay.
right?
Okay.
Well, this is more straightforward. If you add an axis, and this is the angle, right? So, for example, you can write x and 1 here, right? Then super crystal clear,
Okay.
right?
Okay.
Yeah, they have different set of information. The one I suggested is how it's on the tree, how it's oriented on the tree. While what you showed here is you focus on the engraved line.
Yes.
Okay?
And the figure one I have like that's why and if I go back I have it here how it they arranged in the tray.
Right,
So
right.
X and Y. That's
know.
So I have to.
Hey, Mark, listen, I know, like, it's okay to repeatedly, so for, especially for those important information, right? You repeatedly
Sure.
clarifying, right? In all different ways, right? On the tree, the grip line, that's useful for the reader. It's like, writer paper is really like teaching.
Yeah.
It's part of it, right? You teach people, teach the real, you learn first, and then you teach people. And when you teach people, you have to repeat. You just say it once. You know what I mean? Right?
Yes.
You just say it once. It's just they want to get it immediately.
Yeah.
Right? Yeah, that's good. That's good. This is wonderful. Maybe it's a little bit small, but can slide it down.
So I think
It's not
it's either 9 or 10. So it's 10. I think this because it's like
yeah.
A4 image.
That's fine. That's fine. It's
Yeah,
fine.
I just skipped 2 pieces.
Let's move on. Let's move on to the next.
Okay, sure.
Yeah. This simple. Appropriate tip. And then to sample cross section. Recommendation line. So you mean this is the indentation line, right?
Yes, the points, the dotted line. Yeah.
Then maybe at the arrow or whatever
Okay.
indicate, right? And this dashed line, you actually see this surface is actually this surface, am I right?
No,
No?
no.
Yes,
This is the front view and this is the side view. This is the cross section area. That's why it's different. Like.
So what you are showing is the cross section.
Yes.
What's the point? What's the point you want to make? You want to make.
So I want to show that the lines like it's not clear, like it's sharp edges between these two materials. You can see there is some like interface coming or like an area of transition between them.
Not 100% clear line, right?
Yeah, so they are not. Yeah, when they're printed, you can see like, okay, this is white, but at the end, there tend to be there is like some mixing here.
I see.
Like we designed the sample to have sharp lines, but we don't get that in the printer. So this is the whole point of the indentation.
I see. It's also a little bit tilted. If this tilted, right? It's a little bit tilted. It's not very
Yeah.
right?
Okay.
So if this tilted, if you don't want to comment anything about this tilted feature, you rotate the image so that it shows as the horizontal. Okay. Then people will focus on the boundary between the layers instead of its tiltiness, right?
Should I comment anything on the like in the figure as about the boundary, like fuzz boundary or something, or like should I leave it in the text?
A boundary of what? Of
Like here, at the boundary between the layers, should I write like um,
boundary
showing the
between
boundary between the layers, or like fuzz layer boundaries or something like that?
Or you can circle it if that's what you want to say. For example, if you want people focus on
Mm-hmm.
here,
Okay.
right?
Yeah.
You can circle and give t equal to a number, right? Is equal to what number? Because you don't have a scale bar.
Yeah, I have it here as t equal to
Oh, right. Yeah. You can write on the figure as
Okay.
well. So we have this low cell, right? This is such a nice.
Yeah, I did it from the SolidWorks exactly like what we have it in the setup.
Oh, you got it from so you built it yourself?
Yes.
Really, that's a very high quality
Yeah.
image, right? Very impressive. So the width of the sample is
2 mm.
usually when we show an optical image or SDM, we will put a scale bar here.
Okay.
So, yeah, it's perfect. It's perfect. You know, this image, you can make it a little bit larger.
Okay.
If that agree, if you want to, that's the point you want to make.
Yeah.
And those ones you can shrink a little bit if they need more space for this guy.
Okay.
Right?
Okay. Got that.
Okay. Nano indentation. Well, indentation measurement. This D is not nano indentation.
No. This is I thought it like it's not the figure caption is not.
You do not need to have everything. You can directly start from A is what, B is what.
Oh.
Make sense?
Okay.
But if they are not connected, you know.
I could say like mechanical experiments, and then A is nano indentation, and then
Yeah. And you can say setup, right? Mechanical experimental setup,
Okay.
right? And then A is a nano indentation, B is a microscale, right? Microscale. It's a unique expression, right? Microscale. Make sense? Mm-hmm. Yeah. Also, FD model. Interface model. Intelligence. Interface. Effective stiffness is actually Poisson solution. Those curves are schematics, right?
Yes. Just showing like the different fiber orientation for the rule of mixture.
This curve is the rule of mixture.
Yes, as a function of the fiber orientation. Usually the rule of mixture is a function of volume fraction, but I got these two curves from the book for the composite material.
Well, it doesn't have a vertical axis.
These are like the E max and E minimum for, like this one could be for the fibers, like stiffness of the fiber, and this one is the minimum. Like it's from the. Let me show you. How can I want to go here? Chapter 4. This too.
No,
So
they do have a dimension. Right?
These
It-
ha-
it- mm.
but these are for specific material. So
For specific material, that only means, I think, what is E2? E2 is the matrix,
yes,
or what?
Yes.
E2 is the matrix.
yes.
Right. So this only means they know the ratio of,
Yeah, it's based on the ratio between the two materials, I think, or like.
right. I think what is known for this one is E1 over E2, right?
Mm-hmm.
This is known, so that means that this is for this specific material. That only means this guy is known, right?
Yeah.
Right. So can you, yeah. So you basically you have an equation. Do you want to provide that equation?
Okay. Okay.
No, I'm asking because I don't know what you want to say. If you do that here, if you go back to that.
Okay. So let me go. I will show you. So for this one, I want to show that we're gonna use the rule of mixture for the interface here. That is our model for the interface. That we're using the printing direction here at angle as it's like a fiber directions here for the rule of mixture. So whenever the printing direction is changing in the interface, because the two base material, pure white and the azureous black, are isotropic. So the only anisotropy we have is interface here. So that's why we have different values for the stiffness and the Poisson's ratio. And we are gonna model this interface as a rule of mixture. A rule of mixture is like usually applied for the fibers in different directions. So here we have like an analogy from the fibers direction to the printing direction. And I want to show like in the rule of mixture how the stiffness is changing as a function of the fiber orientation.
I see. So this is a printing direction, right?
It in our case it's a printing direction, yes.
Okay. So this is a printing direction.
Yeah. So this here I have beta and here is theta. So that's why I changed the angles.
So you model the interface as a fiber matrix composite.
Yes. That's what the plan that we had. This is what we did.
Do you need that? Oh, that's a model.
This is the model for the FAM. Yes, this is what we did.
Mark, so I like discuss this later. I just feel we
Okay.
do not need to show this, a figure like that.
Okay.
Because later we will have the real data we have to compare. This is like always our reference or say some theoretical prediction, right? Well, if we just show it like this, it's just not very.
Okay.
People usually don't do that. That's why I feel a little bit weird. I don't see people do something like that.
Okay. Okay.
So you use this figure to show how you are to reasonable life, the way you model the interface.
Yes.
Okay.
Yes.
Mhm.
But yeah, I will think about this.
Mm. See, this figure does not show that printing direction effects.
Which
Am I right, or do you think, or how to look at it? You know, this is if I want to reasonable lies, okay, that's why I assume here is the along fiber direction, right?
Mm-hmm.
I may put those circles, those dark green circles, make sense? A little bit look like along the
Oh.
direction,
Oh. Okay.
right?
Yeah.
Have a little bit, there are some randomness, but have some a little bit of indication, right?
Yes. That
The
is.
pattern would somehow support your, this is not a real figure, it's still your hypothesis or
Yes.
your kind of reason,
Mm-hmm.
right?
Mm-hmm. Mm-hmm.
Make sense?
Yes.
Okay.
I could, like, if you think we could have something else instead, if you think um, I'm not sure where is my SCM images.
I see some dots in somewhere,
Yeah, I want to show the. Oh, yeah, I think it's in the non-indentation. Non-indentation, I think it's either here or the other one. Not this one. Or this one. Oops. Where's the presentation for this one? Yes, something here. So this image shows the droplet, like instead of having a schematic, I could add something like this if you think this is suitable, like here. Is it better to have it as schematic or like as a real picture of what's going on here, of the directions, droplets?
I need to know this image, where is the design line? Is it here? This is the design, roughly speaking, right? The layer direction.
So it
The design, the layer direction.
no, it's it should be something like here.
Oh, this is the design, the layer direction.
Yeah.
What's the printing direction?
So it's here.
Are you sure?
Or it's,
I think
I think it's the
it's opposite.
yeah, it's
This
the
is
opposite. Sorry,
direction.
the printing direction is this way, and the design layer is this way. Yeah.
It's horizontal or vertical?
At this point it's the same.
Why does it look like vertical layer?
I did have the comments on this one, but yeah, I'm not sure. So it might.
You have to be very sure.
Yeah, I think I need to make sure which one is it. But what I have is like the printing direction is 45, but yeah. So if this is X, this is 45, and then
You know, if you put a cartoon, if you figure it out, put a cartoon here, right?
mhm.
To show the layered design.
Okay, yeah.
The layered design. Look to me is vertical, right?
I think
Then, yeah.
okay, and then I can yeah.
Right, you can, you know, if you put this figure, and then that will mean this is like an interface that is, you know, to have those dots.
Yeah.
Right?
Yeah.
So, well, it's interesting. It's not like everywhere. It's not like here they don't have it, right?
Yeah, the dots are not like. I think Professor, is the distance maybe between each pass. So each pass, like if we say of the printer, it was like point. I think if this one.
So do you try to say these dots are like those circle dots you draw, right?
These are happening in the. This is the texture of the soft material. We have this dot. Yeah.
So this is like millimeter size, where the dots. The dots diameter is about a millimeter, looks like.
Yeah.
Oh, sorry, 0.1 millimeter.
Yeah.
Right?
Yeah.
0.1 millimeter. Okay. Our interface was 0.1, 0.2.
It's 0.15 to yeah 0.2.
0.1, 0.2, 0.4, 0.8.
The design is 0.2, 0.4, 0.8. The design thickness.
Okay. Yeah, I think this is reasonable. Yeah, this is good image to show. You can put this guy here.
Okay, I will do it and have schematic next to it.
Or here replace it to support the idea.
Okay.
And you can also change a little bit. For example, this you just change the feel of it. For
Yeah,
example,
yeah.
This guy change into dark green.
Okay.
Right?
Yes.
And not everybody like this guy change into dark green, or this guy into white. Right?
Yeah.
Then it shows a little bit of flavor of that orientation. People can tell a little bit about that orientation.
Mhm.
But not exactly either. Right?
Okay.
Yeah, and then together with your SEM images, you can further support that assumption you made.
Okay.
Right?
Okay. Then this is the. So this is for the nano indentation results, and this is
Oh, you have this one.
this is for the soft phase and the hard phase. This is how the structure is looking like. So
Okay.
yeah.
I'm trying to understand if you go to the SEM image you showed, why they were so far apart, you know, those dots, those slant dot line, right? On that SEM image.
Yeah.
Why they are so farther apart?
So for
Not
this one, yeah,
not this one, but these are pretty close, right? Those dots. Make sense?
yeah,
Those dots are pretty close. Well, the other one you showed me not on this slide, but from a different folder.
yeah, this one.
And this one.
So I have
See this?
this one is 60x, so the magnification is 60x, and this one is 35, so it's like far away from the, and these are for different thicknesses as well. So this is C is so for this one I zoom in with an area that has close up dots. Um, and
tell me,
yeah,
still is not because of that. You can see this, the distance between these two is less than the size of the dot. If the size of the dot is the same, you know what I'm talking about, right? It's evidently denser than, way denser than the one you showed me just now. Okay? Well, I don't think it's about, it's still denser, real quick, because the distance between these two lines is about just the size of the dot.
yeah.
Right? Well, the other one,
yeah.
the distance between lines, that's many dot diameters, right?
Yeah, that's true.
So this is 0.8, so this is 0.8 millimeter.
Yes.
Right? So this software there is 0.8 millimeter,
Yes.
right? Here.
Yes. I mean, I can show you. This is the image I got. This is for 0.8. You can see like there's some areas where dense. Close up. This is again for 0.8. I try to measure it here. This is the end of the sample. But for 0.4, yeah, this is for 0.4. This one, if I'm not mistaken, this is where we had like, if this is the one specimen, what is that? The layers are coming this direction, so and the other one was the layer is coming along this direction. So for the printer, it's for one pass it's just changing from soft to hard, soft to hard. For the other one, it's only like soft, 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 soft in one pass. So it's all soft in one pass, somehow. And then when one pass, it's gonna be all hard. But for this one, it's changing hard to soft, hard to soft, hard to soft every time it's going in the pass. Maybe that's one of the reasons why it's different between this one and the other one.
So why? I think maybe we just use the other one.
Yeah. So for now, we can ignore this one.
You
because-
can ignore this one.
Yeah. So.
Yeah.
And then, so.
Right. I mean, you can just using the change the dot without. If you go back to the previous.
Yeah.
The previous image, previous figure.
This one?
No,
Oh,
I mean,
the same?
slide,
Yeah,
the
yeah.
previous slide. Previous slide.
Oh, yeah,
I mean, then just change the dot and you can
yeah.
see
Yeah,
the-
yeah. Okay, I will change it. Yeah.
Like for example, if you move this guy downward, this guy can become up, like move this way. right?
Okay.
Mhm.
Where's the mouse? Okay. And then this is.
Yeah, yeah, this is nice. Yeah. So region one, region two, and region. What's the difference between region one and region two?
So this is going from the soft material to the hard material, and then from hard to soft. Like it's, I'm transit.
Oh,
Yeah.
one is the printing direction this way.
It is zero direction. I didn't change that. So for the for the non indentation we use like the same. Because
The images you show give me impression is printing along this direction.
no,
Right?
you're talking about the SEM or for the non indentation.
I see on the images here. I mean, are you able to see what I'm drawing?
Yeah. For this one, yeah, I'm not sure about the angle, because I'm not showing.
I mean, you do have to be sure. So those are the dots, and we somehow connect the direction of the dots with
Yeah.
the direction. Am I right?
Yes. Um,
If that's the case, you can draw a printing direction here.
okay.
So then this will further support your previous message from a figure. Okay? When you draw those dots and you assume it's a layered structure,
Yeah.
right? Well, this further
Okay.
so what's a region one and the region two
Mm-hmm.
are our interpretation. We expect they are similar, like symmetric, right?
Yes. So like the thickness is different. Like this one is, it's between roughly, like we can say roughly, but it doesn't have to be symmetric. And the other thing is like going from hard to soft or soft to hard is, I didn't continue, but maybe it's the trend is the same, like going from hard to soft or soft to hard is giving you the same distance. That's one thing. And the other thing is so like the point is I want to show the gradual change as well before it's stabilized. Like it's not a sharp increase, just with an angle here, and the same here, just.
Okay.
Okay. And here are the the result of the
Again, what's the printing direction? Like, for example, the image you're showing, right?
So for this one, my comment is that for all printing direction and all thicknesses, the fracture mode is the same. It doesn't change. Yeah.
Okay. So then the printing direction doesn't influence the failure mode.
Yes.
Right. Good. Yeah, good. I mean, if you want to show that more extensively, you can show, for example, this is printing direction, like 0, this 45, or like 30. You can show some of them, then you can say they are the same.
Oh, okay.
Right?
Okay.
Instead of just tell them, see they are the same, like this, right? Then it will be more informative and more convincing, right? If you have those data.
Yeah, I have all the data.
Yeah, then why not put it there? That's a lot of work you did, right?
Yeah. Okay.
Like for example, this is the printing direction, this is 0.2, 0.4, 0.8, right?
Yeah.
And then let the reader make a conclusion. See, they are all filled this way,
Okay.
right? And then when you make a conclusion, it's much stronger.
Okay.
Yeah. Yeah, green.
And the last thing is the simulation that I'm redoing right now because I'm not convinced by this one. So I built the model again and I'm trying different things right now. So I will improve it for like the old one. There's some things like in the mesh, in the materials and everything. So right now I'm working with that here. So once I get the result, it's gonna be a few days. I will show it to you, and then we can discuss it. But this is the old one, yeah.
This is the result for.
Yeah,
this
for
all
the
results.
yes, this is the old result.
So those results, how is different from the previous slide? The result from the
This is
previous
that
slide?
this is that results from the experiment. It's not simulation.
Oh, okay. That's from experiments. I see.
Yeah.
So the conclusion is what?
To be honest, I don't. I'm not sure. Like our hypothesis is that okay, for bond 2 it's consistent because it's all mixed up, like the two materials mixed up, and then the entire area is an interface. And then for bond 4 it it should be the most one with the variation in the results. And then point 8 is going back again to being consistent, but the results are showing something different. Like I can see here for point 8 it somehow has the highest variation. Even you can see it here for the effective stiffness as a function of the thickness, the point 8 has the highest variation. And like I'm talking about this thickness, but about the Boson's ratio, they all changing dramatically. Like
That was so that is 0.8, right?
yes.
So think about the analytical model. Your stiffness is visible. This is the printing direction, right?
Mm-hmm.
This is basement, right?
Yeah.
Well, if so, we're supposed to see a trend like that. If like
Yeah. It's,
no, sorry. I don't want to mislead you. I'm not expecting to see that, but I'm trying to see how that thing. Because if that's assumption made, right? At least the interface will follow.
yes.
Such a plan, right?
Yes. So it's here.
Mm-hmm.
So the interface for the stiffness here is following somehow that assumption. It's gonna be between 0.01 and 0.02, as like the stiffness is in between. This is the blue one is the experimental part, and the green, like the dashed line is the simulation. But for now, let me work on that again and see if I can improve it. But for the experimental part, I think we need to go back and analyze it more for our hypothesis. Like, I had the here the figure set is it. I have the raw data. The raw data shows here. So this is for point 2, point 4, and point 8.
So the point 8 was this D and H was the difference.
Oh,
Well, in
the
reference place.
yeah. So we eliminate this one for now. For the paper, we eliminated
I
them.
don't know
Can add it in the thesis.
why we didn't do. Oh, because we don't have model.
Yes.
Right?
Yes. But
No,
you,
don't say this. Because we don't have model. I mean, how you
yeah.
like we have also so this shows the point 8 have a large variation when the pull along that direction. See, this makes sense to me, Mark.
In which way?
See, we do the data do make sense to me. Like, see this point 4,
Mm-hmm.
it has a large variation.
Yes.
See, this variation is due to the material mixing. Okay?
Yes.
It has the, we assume it has the, and both have strong material mixing effects. Okay?
Yes.
That interface have a huge influence on body. So
Yeah.
when the material is mixed, it's mixed randomly, so the probability have those uncertainty. Make sense?
Yes.
Well, this point 8, that interface become a small contribution, a small volume fraction. So it's more consistent.
Yes. This
Okay?
is our hypothesis from the beginning. Our
Right, and this data does reflect that.
Yes.
Okay? Well, in the longitudinal direction, in this direction,
Point 2 is more consistent, like in the
consistent in terms of the fracture spin.
yes.
Okay. Well, then for the point 8 is the most unpredictable fracture spin. So is there any trend if it's 90 degrees and it's 0 degrees? So the printing direction, that beta angle is this beta angle.
Yes.
So when they fail by break the hard fiber, hard layer.
It just fracture, like all of a sudden the two parts separates.
Separate is like the crack goes through the pretty much perpendicular to the layer, right?
Yes.
So I think I have an explanation, which means if the crack will initiate from the weakest part, right?
Mm-hmm.
And then propagate. What it actually will initiate from the softer part, and softer layer, since that's the weakest. But when you propagate to the hard part, the interface will or the other way. For example, maybe the other way. So when the hard face breaks,
Usually hard face break first. Yeah. But I think like in what I can see from the images, for the longitudinal direction, the interface is a weak spot. Maybe that's why we have the variation and the 0.8, which is the opposite in the point, like the other direction, and the transference.
Yeah. It is possible, for example, this is a printing direction. You have, if you draw your using dots, right? If this is beta equal to 90 degrees, right?
Yes.
This, what I'm doing, this beta. So the crack can easily go through, right?
Yeah.
This is the hard layer. So this is the hard layer of hard,
Mm-hmm.
right? And this is the interface and the other.
Yeah.
For example, either way, either the crack initiates either from the interface or propagated to the hard face or the other way around, right?
Mm-hmm.
This will create a very easy crack propagation path, right?
Yeah.
And that's why this becomes very
Easy to break, like
big, right? Well then the most tougher, or say the long damage was when beta equal to 30 degrees. Well, is there any study on crack propagation? Right. So, for example, for the layered signature,
mm-hmm.
so the crack will more prefer to propagate through the layer, right?
Yeah.
But sometimes, since the loading have a certain direction, right, it has to go through the layer.
Yeah.
Right.
Yeah.
Well, then the orientation of the layer matters for how the crack is going to propagate, makes sense, in which direction. So I think there are certain theories related to explain how the crack is going to propagate. If you read the Nature paper,
Okay.
the Nature papers,
Mm-hmm.
the earlier work by Francisco Bachelet,
Mm-hmm.
the guy who did a lot of work on Nature, right? So he did a study, how the crack, because Nature is like a layer by
Yeah.
layer, right? So he did come up with a criteria. I think it's Nature communication paper by Francisco Bachelet,
Mm-hmm.
talking about the crack propagation in layered nature-like
Okay.
material, right? So that makes, so my point is this 90 degree is the weakest, that's obvious. While there, if that's the case, can they conclude the 0 degree will be the strongest, I would say, more conductive, but it's not.
It's
Make
not.
sense?
Yeah, it's not.
Yeah. So it have a certain angle. I think that paper made an argument. It makes sense?
Okay, I will read it. I will read it.
So I think that's useful. That's useful for us.
Okay.
You can try to find that paper. That's
I can like find it today, and we can meet again tomorrow, like after I read it and see
okay.
if you have time tomorrow to meet.
Right. For example, if the modeling results are not good,
Mhm.
if we can give a in-depth explanation on environmental data,
Yeah.
also effectively, right?
Yes, I think.
And experimental data are valuable, very valuable, because that's real, right?
Yeah. Yeah.
Yeah. So can we go to, so we are somehow like stack at the model
Yes.
and what
So the only
not
thing is right now is like just explain the behavior here and then the model. The modeling.
I think the stress control we can explain roughly qualitatively at this moment, right?
Yes.
If that crack propagation part can have some quantitative analysis.
Yeah.
If you read his paper,
Okay.
his paper is just one equation to indicate the crack propagation. Well, you didn't see the crack propagating in different directions, right?
With the speckle button, it's hard to see it. Like.
Yeah. Find that paper and we can take a look.
Okay. Okay.
And Greece school for there was the advanced material paper. The first author is Greece school. Greece.
Okay.
Who is GU. Who is GU? Her last name.
Okay.
So that paper also has some.
Explanation about the layer crack propagation.
And
Okay, I will search about them today.
these two papers,
Okay.
I think that's helpful.
Yeah. Okay.
I think the environmental data are very good, very reasonable. The model data is
Yeah, the model is still like.
so. So tell me, the modeling approach was using the PNV model for soft and the Bergstrom.
The Bergstrom for the soft and the TMV for the hard.
PNV for hard,
Yeah.
right? And then the interfacial layer, right? So that's the key. So for the interfacial layer in your IPV model, right? How was it modeled?
So we model it as transversely isotropic material.
Transversely isotropic
Yes.
material. So that means you have a material orientation in that interface
Yes,
layer,
exactly.
right? Well, then all the dimension of the interface, the dimension of the interface layer was 0.4, right?
So no, that's why we have here different.
Oh, you have different results.
Yeah, different
right?
results.
These are all model results, or either any environmental data.
So the
Oh,
blue line,
is
the yeah, the
experimental data.
solid line is the experimental data.
So see, that's not bad actually. So is this stiffness? This is stiffness.
This is the.
So what are those curves?
let me-
It's not bad the first row.
Yeah. Let me go
The first
here.
row is
I have it here. I think with all the. Um, let me just stop here. Let's say I need to have it. I think it's in the paper. So this is for point 2. I modeled the entire gauge length as transferably isotropic here, and this is for point 4, and you can see this is the interfacial layer thickness. It's like either 0.1, 0.15 all the way to 0.2.
So can we go this is the stiffness and
Forget about the bottom section. This are like not accurate.
I think stiffness see we capture the level of very good, right?
Yeah, so there is a limit
Like a
between.
range,
Yes.
right? We capture the range very well. And then, yeah, it makes sense to me, to be honest. Right. Even the trend, see, when is 0.8, this trend, when is 0.8, this trend in experiments was not obvious because the interface was some chaos over there.
Yes.
Right?
Yes.
So that trend not necessary. Our model was kind of rigorously define the thickness of the interface, right?
Yes.
Well, for that part, it's chaos anyway, so it's a small portion anyway, right?
Mm-hmm.
So it doesn't dominate the trend, right? It don't dominate the trend, The analytical model, or no, the numerical model give us the trend which dominated by the interfacial direction, the interface direction.
Yeah.
Right? Well, experiments, there are many other factors
Yeah.
could influence the result, while the interface influence is small, right?
Mm-hmm.
That's why we didn't expect it's going to show that trend clearly. Make sense?
Yeah.
Well, for others, for point 2, the trend was even pretty nicely, right?
Yes. Yes.
The trend, like the linear direction was somehow like follow this way, right?
Yeah.
And if you go to point 2, can we take a look at point 2? Yeah, see the point 2 also captures that trend, right?
Yeah.
Well, I think this is reasonable, very reasonable. We can say the it captures, makes sense, and we can explain.
Yeah, it captures the
Right.
limits of the interface that and the influence of that.
It's like it's like the interface, the interface. We model the interface as a layered structure to take into the printing direction effect. Okay. While for when t is small, that will become dominant. Okay.
Yeah.
That effect become dominant. Makes sense. And it is, right? Well, when your layer becomes thicker, that effect won't be dominant anymore. Makes sense?
Yeah.
And that's exactly what is reflected here. How do you feel?
Yeah.
Right? Yeah, I think it makes a lot of sense. Now, Poisson's ratio, I think we did a pretty good job as well. So what Poisson ratio did we use? We use for soft and hard.
For the model, you mean?
Right, in FE simulation.
Yeah, it's the same. We use the rule of mixtures as well.
But what's the Poisson ratio for soft and hard?
Oh yeah, it's like I got it from the experimental part. So for the Agilis Black is around 0.49 and this one is like around 0.3. So this is between the limits between 0.3 and
Only 0.3? I
So-
was a little bit suspicious about the 0.3
For-
for Viride.
for what it's
So here is my question.
Mhm.
For example, if you in your FE model, if you change the Poisson ratio of Viride from 0.3 to 0.4,
yeah
okay,
yeah
will that significantly influence the Poisson ratio? I mean the predicted Poisson ratio from FE results.
I haven't tried that, but it
You know, if you
might.
scroll down, right? If you scroll down,
Mhm.
my question is, scroll down, right? So, I see a consistent difference between
Yeah.
that indicate it's not the printing direction, but the soft and hard material Poisson ratio. You know, for example, if you change the hard material into 0.4 from 0.3 to 0.4 Poisson ratio, will the data all go up?
Yes.
Okay, ma'am?
Yes.
In view, right?
Yes.
So you did you get what I'm
Oh
talking
yeah.
about,
Yeah.
right?
Yeah. Okay.
Because from my experience, I think very wide we were keep using 0.4 in all papers.
I think it's yeah.
Although in those papers it doesn't matter that much.
Mhm.
You know
Mhm.
what I mean? Right.
Yeah.
So we don't actually know, but you measured it. Do you think that's worth to check?
Yeah.
I mean, you do not need to do all of them, right? Just pick one.
Yeah.
Okay.
I kind of picked up 0 and 90 and see.
Yeah, and if that's the case, maybe, this look like we are tweaking.
Yeah. You can see here, Professor, like the Poisson's ratio for Y. This is the Poisson's ratio for Y. It's like it's not 0.3, but I mean it's like 0.35, 0.34, and this is for the Agilis Black. So yeah, it's either I increase like for the one of them, but I will see. I can take the average for both of them. I don't remember, like it was a long time ago, 2 years ago, but I can take the average for all of them and then see maybe that will shift that curve.
Yeah. Maybe. Okay. Very good.
So if I finish the papers, reading the papers today, I will contact you tomorrow. If you have time, we can meet again
Yeah.
and discuss that.
Yes.
Okay. Thank you so much. So I think Shujing is here, so I will leave
Yeah.
now.
Sure.
All right. Thank you, Professor. Really appreciate it.
This is very nice. I think we can finish this.
Yeah, I have the deadline, so I will finish it anyway. So
Very good.
thank you so much.
Bye.